Okay, so let's take a closer look at this specific example and work through what we've laid out as principles for how to approach a pedigree problem. First thing we need to do is determine the mode of inheritance. That's primary. Once we have the mode, we can fill in genotypes, and once we have genotypes, we can start to work on assigning probabilities. Now, the first thing that one should notice when looking at this pedigree is that we have affected children of unaffected parents, so this must be a recessive of some kind. The next thing to notice is that we have an affected daughter of two unaffected parents, which means that this is autosomal. And more specifically, that it's an autosomal recessive. So there we go, we've got mode figured out. Then we just need to assign and define alleles to represent what we're talking about. I'm going to say let big A equal unaffected. So a big A with a dash like this just specifies that it could be big A, or heterozygous. And then I'll say little a gives us the affected individuals, so either gender. So it's autosomal, it's recessive, and now we can start to fill in genotypes. So let's start with the affected individuals. They're the simplest. We know their full genotype right away. And from there, it's just a process of extrapolation and logic to fill in as much of the rest of the pedigree as we possibly can. Now, what can we conclude about this individual? Well, they have to have at least one big A, because they're in this category here. They're not affected. But they have a daughter who is affected, and that means that they must also have a little a, and that applies to both individuals there, and also here. Okay. Now, this individual here, coming from these two parents, well, what can we conclude? Well, they have to have at least one big A. But then for the second allele, we can't be certain as of yet. They could either be big A, or they might be big A, little a, depending on what they inherited from their parents. So for this individual, we'll have to leave this for the moment and then come back and actually assign a probability to the possibility that they're a carrier. This individual here, we know that they're at least big A at this point. Let's see if we can do any better as we work our way back. Now, this individual is heterozygous. So that means that at least one of these individuals is a carrier. Now, most likely it's this situation here where one is homozygous dominant and one is a carrier. And that's because in this case we're dealing with something that's a rare condition. And because it's rare, we're always going to look for the fewest possible recessive alleles in this case. If it's a rare condition, then the allele that gives us the condition is rare. And that means we need to try to minimize the number of individuals in the pedigree that have that rare allele. So technically it would be possible that these individuals would be both carriers, but that's not likely given the fact that it's a rare allele. Now, it could just as easily be the other way around, like this, and we wouldn't have a way to tell that apart. So for convenience, until we get more information, or if we ever get more information, we'll just simply represent it as this, but it could be the other way around. Okay, so now we have these two individuals that may or may not be carriers, and we need to assign a probability to the possibility that either is a carrier, and that's what we'll do in the next step. Okay, now that we've solved the pedigree thus far, we need to start working on the probabilities for these two individuals. So this is individual generation 2-2. So we could ask this question, what is the probability that individual 2-2, oops, and represent it like this. So this is a statement that says, what is the probability that individual 2-2 is heterozygous? And if we put that in a bracket and put a P in front of it, that's asking the question, what's that probability? We also have to ask the question, what's the probability that 2-3 is a carrier? So this is where requirements and the probabilities of various requirements becomes important. Let's start with this one here first, the probability that 2-2 is a carrier. Okay, Let's look at their parents and draw the Punnett square for their particular mating and their offspring. Okay, we know that they're both carriers because they have an affected daughter. So that means that their possible offspring could have these 4 genotypes. Except now when we look at this individual, we do know something more about them. We know that they're not affected, which means that they cannot be this. In other words, we're left with these choices to choose from. So the question is, how do we assign the probability that this individual is a carrier now that we know we can exclude this particular possibility? And this is called normalization, and it's very important. And you need to learn how to do this properly, especially because this particular example is quite simple, but in later pedigrees the example will be more complicated. So the way that this is done is we take the original probability and then we normalize it relative to the remaining options. So if we had just taken this little Punnett square at face value and say we didn't know anything about the phenotype of this individual, we would say that the probability that this individual is a carrier would simply be, again now using the product rule as we've been talking about, right? This would have a value of 1/4, this would have a value of 1/4, and then we would add them together using the sum rule to give us this probability of 1/2. Now this is 1/2 out of a total of all different possibilities. But now what we're going to do is we're going to remove this possibility, and this possibility also has a value of 1/4 in this overall Punnett square. So the way that that works now to say, okay, the probability that this individual is a carrier now has to be normalized relative to the fact that we've excluded this option. So instead of saying it's 1/2 out of a total of all possible options, it's now 1/2 divided by the total possibility, subtracting everything that we've eliminated based on its phenotype. So 1/2 divided by, in brackets, 1 minus 1/4 is the same as 1/2 divided by 3/4. Now if you remember your math from high school or elementary school, that's the same as flipping this over and multiplying. So 1/2 times 4/3, which is the same thing as 4 divided by 6, which is 2/3. Now you might ask yourself the question, well, there were just, there were 4 squares in the Punnett square, and we got rid of them, so now it's just 2 out of these remaining 3. That only works in this specific example because each of these squares has exactly the same probability value of 1/4 each. You are going to be soon doing problems that don't have that setup, where you have squares in the Punnett square that have different values. So this is the proper approach to take, not to do any kind of shortcut based on just what squares you're eliminating. Use this method, and this method will always work. So this now gives us a value for the probability that this individual is a carrier. So we can say they have a probability of being a carrier is equal to 2/3. In the next step, we'll tackle this individual's probability.